Oh, so this is your learn from home lesson. We are going to do the second part of the fundamental theorem of calculus and also learn about what an accumulation function is. So this is your first part of your fundamental theorem of calculus, which is your integral of a derivative. So to remember, derivative means slope, integral means area. So this is area under a curve. And it looks like this. And I didn't change to a capital letter. I kind of don't prefer doing that. I just wrote f prime here and then wrote f of b minus f of a. So it's upper boundary minus lower boundary. So you do an antiderivative and then it's upper minus lower. That gives you the area under the curve. So the second part is derivative of an integral. So derivative means slope. That's a rate of change. This is the rate at which the area is changing. And so there's three different ways that this can look. So that's why I have so much space here. And it's going to say d dx. That's just instructions that mean take a derivative with respect to x. So that's instructions that mean do a derivative. And the letters of the alphabet are actually kind of important here. This is f of t dt. You're going to see t's inside of the integral, but you're doing a derivative with respect to x. So ignoring this part, if you were to do an antiderivative of this and then upper minus lower, you would get a numeric value, something that represents the area under that curve. And so it would be like 7 or 5 or 12 or -3 if it was below sea level. If you do the derivative of just a number, you get 0, which means it's not changing. It is constant, so it is not changing. So if both of your boundaries are just numbers, then it's going to be 0. It's not going to change. So if it looks like this, and you have x as your upper boundary, when you do your derivative with respect to x, the derivative and the integral undo each other, and you just get f of x. There's not a plus c because this is a derivative, not an antiderivative. So essentially, the derivative and the antiderivative cancel out, and you're just taking this x and plugging it into that function is really all that you're doing. And if these are reversed, then you would get negative f of x. It would be, opposite, like the other way. So instead of just x, if it's another function there, here I'm writing g of x, but it could be x squared or 3x plus 2 or sine of x, whatever. If you have something more than just x there, then what you do is, like here we just took this x and plugged it in. You take that g of x and plug it in, so you get f of g of x. But then remember, it's a derivative, so you're going to have to do a chain rule and chain on the derivative of this function. Sometimes I'll even put that first, like I'll put the g prime first to remind myself to do it. So it's kind of like the 3 tiers of that and the way that it can look. That all sounded really complicated, but you're not actually like doing anything. This is one of those things where the only way you're going to mess it up is if you do anything. So watch, it's derivative of an integral. They cancel. And so all you're going to do is take x and plug it in for t. So this is just going to be x squared plus 4x minus 7. That's literally just it. This one, same thing, but see how the boundaries are reversed? It's going to be the opposite of whatever you get when you plug x in. So if I plug x in, I'm going to get x squared minus x. And again, because the boundaries are reversed, you just want the opposite of that. So if you distribute the negative, it's going to look like that. Same thing here, but see how it's not just x, it's 5x? You have to chain on the derivative of the 5x, which would just be 5. And oftentimes I just put that first. And then you just take the 5x and plug it in for t. So it's going to look like that. Here, you're just going to plug x in, but the boundaries are reversed, so it's going to be the opposite. So it's negative sine of x. This one, both of the boundaries are just numbers. So it ends up being 0. Again, if they're both just values, then, the derivative of just a number is going to be 0. Here you have x cubed, so you would have to chain on a 3x squared. Again, usually I'll just put that first, and then you just take that x cubed and plug it in. All right, same thing for this one. Actually, you have two things going on here. First of all, the boundaries are reversed, so we're going to need a negative out front. It's not just x, it's x squared, so you have to chain on the derivative of x squared, which is 2x. But then beyond that, you just take the x squared and plug it in for t. So if you plug x squared in here, you get x squared squared, which would be x to the fourth, and then plus 5x squared. And you could distribute the negative 2x through there if you wanted to. It would look like this. For this one, you have x plus 3 is your upper boundary and just x is your lower boundary. So since they both have a variable, we're going to do upper minus lower. So I'm going to plug the x plus 3 in for t, which would look like that, minus, and then I'm going to plug the lower boundary in, which would look like that. So we just did upper minus lower. And then I'm going to just do the algebra for this. So it'll be 2x plus 6 minus 5, distribute the negative. And then a lot of canceling is going to happen because they both had an x. So, you're going to have a lot of the stuff cancel out. The 2x's are gone, the 5's are gone. And so you just end up with 6. Now, for the AP exam, oftentimes you'll see problems like this, where they don't really give you a whole lot of instruction, so you kind of have to interpret what they're asking for. They give you this f prime, so that's your rate, and they ask you for f of 6 minus f of 4. When you see something like this, you need to think fundamental theorem of calculus. It's upper boundary minus lower boundary. This means integral. So it is your integral from 4 to 6, because again, it's upper minus lower, of this 2t plus 1 dt. So we're going to do an antiderivative. That would be t squared plus t. And then we'll do upper minus lower to get our f of 6 minus f of 4. So again, the reason this is f and this is f prime, we have f prime goes in here. When you do the antiderivative of f prime, that takes you back to f. So when we plug these in, it's f of 6 minus f of 4. So what would that be? 36 plus 6 would be 42. And if you plug in 4, that would be 16 plus 4 would be 20. So 22. This one we're going to use calculator. So actually, hold on a second. Let me make sure I have my Desmos pulled up. I think I do. Yes, I do. All right. So they tell you all this stuff. Here's what they want. G of 7 minus G of 2. So it's going to be integral 2 to 7 of G prime, whatever that is. So now we're going to look back at the other stuff that, oh, sorry, I guess I should have made it T. They're not going to mark that wrong. I mean, I guess it's just a letter of the alphabet. Whoopsie. I looked back here and I saw all these T's. I was like, oh, whoops. All right, so G of 7 minus G of 2. You want integral 2 to 7 G prime of T dt, because when you do the antiderivative of G prime, you're going to get G. So to go back and find G prime, they say G prime of T equals this. 5 minus T times F of T, which is this. I got this problem from AP Classroom. I thought it was super weird that they did it like that. And I was like, oh, we should probably do that problem. So you need G prime to go inside of your integral. And then they put f of t in there. You have to take this and plug it in for f of t. But anyway, we're going to use the calculator for that one. Let me anchor this with my pencil. I don't know if it's going to stay. But let me share my screen. And if you type int, it'll give you an integral. I think it's also in here under the functions somewhere, but typing int is the fastest way to get it. So we want from 2 to 7, and we need a parenthesis. So we have 5. Now it says t. I was going to say 5 minus t, but we're going to use x. And then it is 3x squared. Oops. Minus 4x the third. dx. So we get 1381.25. All right, so that was your second part of your fundamental theorem of calculus. So this is going to be your accumulation function, and we're going to do all the justifications for this side, and then I won't make us write them on this side. We're just going to repeat the process for this twice. So we'll write out all the justifications, and then I'll just kind of do them verbally on the other side. So an accumulation function is a function in terms of an integral. You have to be careful where your accumulation starts. In this case, it starts at 3, which is right here. It is not always 0. That's the common mistake, is accidentally always starting at 0. Make sure you start your accumulation where it says to start. So in this case, it is 3. I'm going to go ahead and break this down and find all of these areas right off the bat because I know that we're going to need them. So before I even start doing any of these problems, let's go and find all these. So this is a triangle, 1/2 base times height. So it'd be 1/2 times 2 times 1. It would just be 1, but it's going to be -1 because it is below the x-axis. This is also 1/2 base times height. Your base is 3. Your height is 5. So that would be 15 halves, or I'll use a decimal here, 7.5. I'm going to break this one right here. This is a trapezoid. It's on its side though. So this is the height and these are your two bases. So for a trapezoid, it's 1/2 times the height, and then adding the bases together would be 5 plus 2. So 7 halves, or 3.5. I'm going to break this one here. It's another trapezoid. So 1/2 height, add the bases together would be 2 plus 3. So 5 halves, or 2.5. Here's another triangle. 1/2 base times height. That's going to be 1.5. And then another triangle, 1/2 base times height. That would be half of 4, which is 2, but it's going to be negative since it's below the x-axis. So I just went and broke that all up, to start out with. So this is our function. G of x is our accumulation starting at 3, and then this is the graph of f. So we are talking about function g in all of these problems, but it says function f is shown to the right. So the first thing that we're going to do is get our derivative. And just like we learned with the sheet that I just did on your second part of your fundamental theorem of calculus, when you do the derivative of this, derivative and integral cancel, you're just going to take the x and plug it in. So when they say that this is the graph of f, what they really mean is that it's g prime. So that is this graph right here. So are you answering questions about this graph? No, you're answering questions about g. This is g prime. Oh, I need to grab a sticky note and rewrite that here. I don't have one. Hold on, I'm gonna pause this and grab a sticky note. All right, so I usually call this f. It doesn't really matter though, so this time I'm gonna call it g since that's the function that we're talking about. So we have increasing positive, decreasing negative, and if that's true from here to here, it's going to be true from here to here. It's true every time you take a derivative. And then the other thing that we can fill out for our second derivative, positive means that your original graph is concave up, negative means concave down. So this is essentially what we're going to be revisiting, except from an integral standpoint. So state the critical points of G. Critical points are where your derivative equals 0. This is our derivative graph. This is f of x, which is g prime, the derivative of this. So where this equals 0 is 0, and what is that, 6. So remember, your sentences start f of x is or f of x has, just in this case, instead of f, it's g of x. So g of x has critical points at x equals 0 and x equals 6. Because g prime equals 0 there. So this is your graph of g prime equals 0 at 0 and 6. So those are our critical points. All right, state intervals where g is increasing and decreasing. G of x, which is not this graph, is increasing where your derivative is positive or above sea level. So that's going to be from 0 to 6. Decreasing is where your derivative is negative. That's below. So that's -2 to 0. And what is that? 6 to 8. So g of x is increasing 0 to 6 because derivative is positive there. G of x is decreasing everywhere else for the opposite reason. Right? The justifications did not change. They're the same as they were back in Unit 5 when we did this. We're just revisiting. So you already know how to write these. We're just doing this from an accumulation function standpoint. All right, state the values where g has relative extrema. Relative maximum is a change in your derivative from positive to negative. So above to below, that's going to happen right here. Relative minimum is a change in your derivative from negative to positive. So below to above. So that's going to happen right here. So your sentence is going to start g of x has a relative maximum at x equals 6 because g prime changes from positive to negative there. And then g of x has a relative minimum at x equals 0 because g prime changes from negative to positive there. So again, same exact sentences that we wrote back in Unit 5. Absolute maximums and minimums come from your candidates test. This will 100% be on the free response part of the exam. They put it on there every year. Last year or the year before, I can't remember which, there were actually 2 of these on there, 2 candidates tests. It will be on there. So your candidates are your end points and your critical points. So end points are -2 and 8. Critical points are 0 and 6. And this is where all of our areas come in. We have to plug these into the original function g of x, which we haven't really looked at much to answer the rest of these. We were referencing our derivative, which is what we're looking at here. G of x is this function. Your accumulation starts at 3. So we want to accumulate area from 3 to -2. If you plug -2 in for your upper boundary. So we want to go from here at 3 backwards to -2. So if you're going backwards, that would make this a -7.5 and then that a +1. So -6.5. If you plug in 0 to this, you want to go from 2 to 0. So again, you're going backwards, it would be -7.5. If you plug in 6, finally, we're going forwards. You want to go from 3 to 6. So from here to here, you would have to add all these up. So what is that? That's 7.5. And then if you go from 3 to 8, well, we just said this was 7.5 minus 2 would be 5.5. So we're going to say our absolute maximum is 7.5 at x equals 6, and our absolute minimum is -7.5 at x equals 0. We did justify, the chart is the justification. So you don't have to write a sentence for it. You did justify it. It's the chart. Inflection points come from a second derivative. So let's look at our sticky note. Changing concavity, it's where your second derivative changes from positive to negative or negative to positive. This is the graph we're looking at, though. This is the one that we have. So a change in concavity is where this graph changes increasing to decreasing or decreasing to increasing. This is the one that's annoying to write. And I've asked about it, like, is there a shorter way to do that? And they've said no. So let's look at our derivative graph, our g prime. We want to change increasing to decreasing or vice versa. So we are increasing. We have a change here. Oh, there's actually going to be a lot of them. and here, and here, or I guess just 3. So our sentence is going to start g of x has inflection points at x equals 3, x equals 4, and x equals 5 because g prime, so the graph we're looking at, changes from increasing to decreasing or decreasing to increasing there. All right, concave up and concave down. G of x is concave up. Let me pull out my sticky note again. Concave up when your derivative graph, the one that we have, is increasing. So wherever this graph we're looking at is increasing. So that'll be -2 to 3 and 4 to 5. Because G prime is increasing there. And then your sibling sentence, G of x is concave down, is going to be where this graph, the derivative graph that we're looking at, is decreasing. So that would be from 3 to 4 and from 5 to 8. Because G prime, that's the graph that we're looking at, is decreasing there. And then what we're going to do here is take all the information that we have and put it together and draw G of x, this graph that we've been answering all the questions about that we aren't looking at. Again, this is G prime. We're going to take all this information, put it all together, and draw a graph of G. So the first thing we want to do is put all of these points on here. You want all the important points. So these are your end points, your critical points, and then we're going to also want to do our inflection points. But I'm going to start with these. So -2, -6.5. Like right about there. I used my printer at home to print this, so my grid did not print very well. All right, 0, -7.5. 6, 7.5. And 8, 5.5. Good enough. All right, so that's the endpoints and the critical points. I want to go back and get the inflection points, which are 3, 4, and 5. So if you plug 3 in, you get the integral from 3 to 3, which is precisely nothing. You have accumulated no area if you go from 3 to 3. So we get 3, 0. And then we need to plug in 4. So we want to accumulate from 3 to 4, which is this section right here, which is 3.5. So we get 4, 3.5. My grid is very bad here. And then also 5. So if we accumulate from 3 to 5, we get these two sections here from 3 to 5, which will give us 6. So we get the point 5, 6. And then basically you just play connect the dots. And you don't really need to worry about increasing and decreasing because to get from here to here, you're going to decrease. To get from here to here, you're going to increase. You don't have to really worry about that. The only thing you really need to worry about is the concavity. So looking here, we want to be concave up from -2 to 3. So I want to be concave up for all of this. And then it says concave down from 3 to 4. It's going to keep switching. So you want to switch there. So do you see this inflection point? We were concave up, then it switches and it bends the other way. Concave down. And then we want to be concave up from 4 to 5. So concave up for this section. And then concave down for the rest of it. So this is the graph of G that we were answering all those questions about that we were finally able to make a picture of. On this side, we're going to repeat the process, do all the same stuff, but I'm not going to make us write all the sentences. And again, I'm going to start by just slicing this all up and finding all of the areas because I know that I'm going to need them. So first, a triangle, 1/2 base times height. So the base is 2, the height is 4. That would actually just be 4, but it's going to be -4. This is a semicircle, so that's 1/2 pi r squared. The radius is 2, so that's 2 pi, but it'll be -2 pi. Here is another triangle, 1/2 base times height. That's just going to be 1. And then a square. I know it's not, it looks kind of like a rectangle, but it is 2 by 2. It's just that this is, stretched a little bit. So that'll be 4. Here's our g of x. Our accumulation begins at -4. So like this is where our accumulation starts, doesn't start at 0. And the first thing we're going to do is find g prime, which you're going to just take the x and plug it in, which is f of x. You have to write this somewhere. They're going to put this on the free response part of the exam. And this is worth a point, is to link those two things together. So, and they usually say it doesn't matter which section you write it in, like A, B, C, D, but you have to link those together, somewhere. So critical points are where your derivative equals 0, g prime, take 2. Been talking too much. This is the graph of f, which is g prime. So this is your derivative graph. Critical points are where your derivative equals 0. So that's going to be -4 and 0. And so the full sentence would be g of x has critical points at these because g prime equals 0 there. All right, increasing and decreasing. Here's our sticky note. Oops. Increasing is where your derivative is positive, that's above sea level. Decreasing means negative, that's below sea level. So your sentence would start g of x is, but again, we wrote them all on the other side, so I'm not gonna make us write them all again here. So increasing would be 0 to 3, because g prime is positive there. Decreasing would be -6 to 0, because g prime is negative there. All right, relative extremis. We're going to say relative max at x equals. Now that's going to be where g prime changes from positive to negative. And actually, I should have looked ahead because I'm just noticing now this doesn't change from positive to negative anywhere. So we're not going to have a relative maximum. Should have looked at the graph first. We are going to have a minimum though. So relative minimum at x equals, minimum is a change from negative to positive. So that's below to above. So at 0, we're going to have that. So that's this critical point. And then we need to mention -4. This is that situation where there isn't a change. So I actually will write out the justification for this one because we didn't do one like that on the other side. So I'm going to say g of x has neither a relative maximum or minimum at x equals -4 because g prime does not change sign there. You can also say stays negative there. I try to stay away from that though, because what if the derivative graph stays positive there? So I like does not change sign there. So that's what I stick with because that works every time. All right, absolute maximums and minimums. This is our candidates test. You're going to test your endpoints and critical points. So your endpoints are -6 and 3. Critical points are -4 and 0. Oops, I just drew on the paper. All right, so our accumulation starts at -4. Just be careful with that. If we plug in -6, we're going to accumulate from -4 to -6. So we're going backwards, like from here to here. So it will actually be a +4. If you accumulate from -4 to -4, you've gone precisely nowhere. If you go from -4 to 0, that's going to give you that -2 pi, which I'm going to just go ahead and approximate that because we have to figure out what's the biggest and what's the smallest. If you think of pi as approximately 3, it's approximately -6. Please be careful with this though and don't put an equal sign there. The only reason I did that is because when we look at this list, we have to figure out which is the biggest and which is the smallest. So you need like an approximate value for what pi is. All right, and then if we do 3 from -4 all the way to 3, it's going to be that -2 pi plus 5. So if we think of pi as approximately 3, this would be -6 plus 5, so approximately -1. So our absolute maximum is, the biggest value we got is 4 at x equals -6. Absolute minimum is, now don't say -6. The only reason I did that is so we could tell which is the smallest. -2 pi is the actual lowest value at x equals 0. So just be really careful with this. You kind of need to do that because if that's not there, you're going to go and look at that and be like, wait, which one's which? So you just do that so you can figure out what's the biggest and what's the smallest, but make sure you put, what the actual value is. All right, inflection points, again, that is a change in concavity. We're looking at the derivative graph, this one right here. So that's where this graph changes increasing to decreasing or decreasing to increasing. So let's go and look at our graph. We have a change here at -4. We have a change here from decreasing to increasing at -2. And then it feels like this one is going to be a change as well, but it is not. And 1 year on the free response, they put all of these constant sections in the graph, simply to confuse everyone, I suppose. But this does not count. You have to have a change increasing to decreasing or decreasing to increasing. Constant does not count. So this does not count as an inflection point. So just be really careful with that because they were really, really, really evil about it 1 year. Right, so just those two. And your justification would be because G prime changes from increasing to decreasing or decreasing to increasing there. That's that annoying answer. All right, concave up and concave down. So I'm not gonna write out the whole sentence. I was just saying the whole sentence for that one, so I was about ready to. Concave up is where your derivative graph is increasing. So that's going to be -6 to -4. And then also -2, still increasing all the way to 1. It'll look like that. Concave down is where your derivative graph is decreasing. So that's going to be -4 to -2. And then if you don't have a bend in the graph, so concave up is like this, concave down is like this. Linear, so like a line, is when you don't have any bend in the graph. And that's going to be from the 1 to 3. So there is no concavity. You don't bend one way or the other. So we're going to take all this information and put it all together to get a graph of G. So I'm going to start with these points, our endpoints and critical points. So -6, 4, and then -4, 0, and then 0, approximately -6, but pi is slightly bigger than 3, so it's going to be like -6 and a little bit. So like I'll just put the point slightly beyond -6. And then the same thing with this one. This would be, slightly beyond -1. It would be like -1 and a little bit. So like there-ish, good enough. And then you have to go back and get the critical points as well. -4 we already did. Or I'm sorry, you have to go back and get the inflection points. -4 was a critical point and an inflection point. So we already have that one. We just need to go back and get -2. So remember where your accumulation starts. Your accumulation starts at -4. So if we go from -4 to -2, that's just this part. And so instead of -2 pi, it's just -pi. So approximately -3. -3 and a little bit. So for -2, we get -pi. So -3.14. And then I know it didn't count as an inflection point, but when we go to do our graph, we're going to have to also put 1 on there because that's where we have a change to this linear section. So if we go from -4 all the way to 1, that's going to be -2 pi plus 1. So approximately -6 plus 1, so approximately -5. So if you plug in -1, you get -5, like, and a little bit. And you don't need to worry about increasing, decreasing. Like to connect from here to here, you're going to decrease. To connect from here to here, you're going to increase. So you don't have to worry about that. You just have to worry about the concavity. So we want to be concave up from -6 to -4. So concave up, concave down from -4 to -2. So do you see how it switches? I don't know. Not really something you can teach. Like you just kind of have to see it. Like this bends upwards, and then here's the change, and then this bends downwards. And then concave up again from -2 all the way to 1. So this portion is concave up. And then we want to be linear for this section. So no bend. So you just connect it as a straight line. Try and get that where there's no glare. That's a little bit better.